Welcome to The Explainer. Today, we're diving deep into the algorithmic magic that really makes modern AI tick. We're going to go on a quest, you and I, to defeat a fundamental computational bottleneck that's at the very heart of everything from self-driving cars to medical imaging.
All right, so here's the plan for our quest. We'll start with the absolute basics. Then we'll introduce the villain of our story, a painfully slow algorithm, and from there, we'll uncover all the clever tricks and eventually the ultimate breakthroughs that give us the speed we so desperately need.
So, to kick things off, let's get a real handle on this core concept. What in the world is this convolution operation that's so foundational to the entire AI revolution?
You see this thing everywhere, even if you don't realize it. It's the same fundamental process that helps a computer identify cells in a microscope slide, and it's also what your phone uses to apply a blur filter to a photo. It's all about letting a small pattern, what we call a kernel, influence a much larger image.
A really good way to think of it is as a kind of sophisticated blending of two sets of information. Imagine you're sliding a small magnifying glass, that's our kernel, over a huge picture. At every single position, what you see through that glass is a unique blended result of the image's pixels and the properties of the glass itself.
Now that cool blending idea, it actually boils down to a pretty neat mathematical formula. To get each new output value, that y of n, we're just taking a weighted sum of the input values x, where all the weights are defined by our kernel, h. It's a very systematic process of multiply and then add.
Okay, let's actually trace this out. To get that first output, y0, we just sum up the first column, -8. Simple. For y1, we sum the second column. -4 plus 16 gives us 12. See how that works? You just slide, multiply the elements that overlap, and then sum them up. Seems simple enough, right? But, and this is a big but, this simplicity is hiding a huge problem. So while this direct method is super easy to grasp, it is incredibly inefficient. In fact, this inefficiency, that's the villain of our story. The massive bottleneck we absolutely need to overcome.
The problem has a name. We call it O of n squared complexity. What that really means is that if you double the size of your input, the time it takes to compute everything doesn't just double, it quadruples. For the insane datasets used in modern AI, this kind of quadratic growth isn't just slow, it's an absolute non-starter.
So how in the world do we defeat this O of n squared beast? Well, our first clue comes from a classic computer science strategy: divide and conquer. The key question becomes this: can we somehow reduce the number of multiplications? I mean, multiplications are by far the most computationally expensive part of this whole operation. If we can just do fewer of them, we can win back a ton of speed. And it turns out the answer is yes. The Card-Suba algorithm is this really clever trick that takes a problem that looks like it needs 4 multiplications and somehow solves it with just 3, just by adding a few extra additions. When you apply this trick over and over, recursively, it brings the complexity down from n squared to n to the power of about 1.58. That's a definite improvement.
But, while Card-Suba is super clever, it doesn't always play nice with the kind of hardware we use today. The real hero of our story, the absolute breakthrough, comes from looking at this problem in a completely different way.
This right here, this is the big idea. The convolution theorem basically tells us that we can trade a very, very difficult operation for a very simple one, if we're just willing to change our perspective. Instead of doing all that sliding and multiplying in the time domain, we can switch to something called the frequency domain and get a massive shortcut.
So how does this magic trick actually work? Well, it's this awesome 3-step dance. First, we use an algorithm called the Fast Fourier Transform, or FFT, to jump into the frequency domain. Then, in that domain, we do a super fast, simple multiplication. And finally, we use an inverse FFT to jump right back. I know, it sounds like you're taking the long way around, right? But trust me, this little detour is a massive, massive shortcut. And what's the result of all this? We've basically transformed our slow, clunky quadratic problem into something that's nearly linear. And O of n log n complexity means that even for gigantic inputs, the computation time grows incredibly slowly. Frankly, this is what makes large-scale deep learning truly possible. Period.
Okay, so we've got this incredible theory. But how does it actually connect to the real world of deep learning and the hardware that powers it all? Modern GPUs.
See, inside a modern neural network, these convolutions aren't just happening once. They are happening millions, maybe billions of times. So having a fast algorithm on paper just isn't enough. It has to be absolutely blazing fast on the actual silicon that's doing all the work.
And the optimization gets, well, really nitty-gritty. It goes all the way down to how you just arrange your data in memory. Even changing the order of the dimensions in a tensor can have a huge impact. A lot of frameworks use this NCHW layout, but for maximum performance, NVIDIA's high-speed tensor cores demand the NHWC layout. Getting the data format right is absolutely critical for speed.
All right, it's time to bring everything together and look at the final results of our quest for speed. Let's see the scorecard.
And really, the results just speak for themselves. The direct method is simple, sure, but it hits a brick wall really fast. Karatsuba is a smart improvement, but like we said, often impractical. For any large-scale problem, the FFT-based method, with its incredible ON log n complexity, is the undisputed champion. No contest.
So we did it. We found our hero algorithm and we slayed the convolution bottleneck. But here's the thing, the quest for speed is never truly over. As AI models become astronomically larger and way more complex, new challenges are always going to pop up. The real question is, what's going to be the next great bottleneck we need to conquer?